Moving on to the materials used for red, green, and blue LEDs. On the left is a zoomed in image of an actual pixel from the Sony Crystal LED TV. Here, blue and green InGaN LEDs have been used, and aluminum indium gallium phosphide or Al-In-Gap based red LEDs have been utilized. As can be seen from the band gap versus lattice constant plot here, for low to moderate indium compositions, InGaN can emit in the blue and green region, and the Allen-Gap system can emit in the red region. And if we take a look at the EQE versus wavelength plot for these material systems, it becomes perfectly clear that phosphide-based LEDs are preferred for red emission. But how about micro LEDs dimensioned smaller than 20 or even 10 microns? Due to high surface recombination velocity, Allen-Gap-based micro LEDs suffer a drastic reduction in EQE with size reduction, and also due to their low barrier heights, they suffer from extreme temperature-dependent efficiency droop. Whereas InGaN-based devices have at least an order of magnitude lower surface recombination velocity, and so the size-dependent EQE lowering is expected to be not as drastic. And due to the high barrier heights in the epitaxial structure, the temperature-dependent droop is reduced as well. For these reasons, we wanted to pursue InGaN-based red micro-LEDs. Now let's look at why we wanted to pursue relaxed InGaN pseudo-substrates. Even with all the advantages that InGaN has over Allen-Gap material system, it has its own set of issues. First being the massive 10% lattice mismatch of indium nitride and gallium nitride, which reduces the critical thickness. Second is thermal instability of InGaN, wherein indium nitride sublimes at 550 degrees Celsius, whereas gallium nitride is grown at 1000 degrees Celsius approximately. So how do we solve these issues? The answer lies in a phenomena called composition pulling effect. So suppose we want to incorporate low indium composition into our films at 900 degrees Celsius. Since the composition is low, the lattice mismatch is low, hence the indium gets incorporated without much difficulty. However, if we want to achieve higher indium composition with this growth condition, for example, by increasing the flow of indium precursor, the indium will desorb and we won't be able to achieve the high indium content films. An approach to achieving higher indium content films would be to lower the growth temperature, but due to the larger lattice mismatch between these two films, the morphology of the film will be poor. Instead, if we have a biaxially relaxed InGaN film as our base, we can get high indium compositions even at higher growth temperatures due to the reduced lattice mismatch between these two films. Hence, a relaxed InGaN pseudosubstrate is highly desired. Soitec is known to be an industry leader in relaxed InGaN pseudosubstrates, and they grow their indium gallium nitride strained to GaN and relax them upon patterning. And since they grow InGaN strained to GaN, the scalability to high indium content is challenging. Recently, they published their results for red InGaN micro LEDs sized 50 micron cross 50 micron with an on-wafer EQE of 0.09%. Our approach is to have a flexible underlayer, which in our case is porous gallium nitride, to achieve micrometer scale elastic relaxation in InGaN films. And the reason behind this choice of material is illustrated in the figure on the right, in which it is shown that with increased porosity, the elastic modulus and hardness of GaN reduces, making it less stiff. The method of achieving this porous GaN layer is via an electrochemical etch chemistry set up as shown on the right, wherein the sample is connected to the anode and platinum wire works as a cathode, and gallium nitride is etched due to the formation of holes on the surface, thereby generating pores within the N-type doped material. On the left is the dependence of the doping versus applied voltage. Since this is a doping selective etch, each doping range has a fixed voltage range in which we would get porous GaN. Applying a lower bias will not etch the material, and applying a higher bias will completely remove the material. The cross-section of buried porous GaN material with different doping values is also shown below. Let's move on to the InGaN relaxation experiment. To demonstrate the idea that InGaN can relax in the micrometer scale, we started out with growing compressively strained InGaN on GaN1 sapphire templates with a buried N plus doped GaN layer. We then patterned them into fins so that the electrolyte can access the bottom N plus layer during the electrochemical etch and porosify that layer. We varied our fin width and applied different biases, and using X-ray diffraction estimated the degree of relaxation of InGaN. As we can see, the narrower the fins, the higher the relaxation due to reduced spatial restraints. For composition pulling effect to work, we need to have biaxially relaxed InGaN pseudosubstrates. So we chose a dimension of 10 cross 10 microns square, which was micro LED compatible. And we chose a bias so that we would be able to achieve a significant amount of relaxation as well. As grown relaxed InGaN layer or GaN on sapphire template can be seen to be almost fully strained to gallium nitride, and we can see that they are vertically aligned. So their lattice constants are almost the same. And what we aim for is to achieve a higher degree of relaxation. So the slanted line corresponds to a relaxed InGaN lattice constant. And so what we aim for is to move this InGaN peak towards the slanted line. And the more it moves towards the slanted line, the higher the degree of relaxation. Now, upon...
What's the slope of the 2241?
Sorry, could you repeat your question?
Or, sorry,
can I continue?
Go ahead and continue. I'm going to ask him to throw the question in the chat and we can answer that way.
Okay. Okay, so what we aim for is to achieve an InGaN peak closer to the slanted line corresponding to a higher degree of relaxation. Now, upon patterning into tiles, there was no difference in the strain state of these tiles. And upon porosification, we were able to get this peak shifted midway between this vertical and slanted line, corresponding to a 50% relaxation, which was confirmed to be biaxial. Here is a top view SEM image, and we can see that the tiles are surrounded by porous GaN material. Now, using this biaxially relaxed InGaN, we wanted to demonstrate the composition pulling effect, wherein we should expect higher indium incorporation for quantum wells grown on the sample on the right as compared to the sample on the left. When targeting blue emission on the GaN on sapphire template, we achieved a 45 nanometer redshift and hence green emission for the relaxed InGaN on porous GaN pseudosubstrates. We also wanted to check the strain state of the regrown InGaN layers, for which we needed layers thicker than quantum wells. So we grew about 100 nanometers of InGaN, again on a similar set of samples, expecting higher indium incorporation for the sample on the right. And for the ease of explanation, I'm going to be denoting the regrown InGaN layer as layer 2 and the base InGaN layer as layer 1. And upon regrowth, the layer 2 can be seen below as being as grown 50% relaxed compared to gallium nitride. This layer 2 can also be seen to be vertically stacked or vertically aligned with layer 1 InGaN, which means that these two layers are logged to each other's lattice constant. And on the other hand, the InGaN grown on gallium nitride on sapphire template was fully strained to gallium nitride. Now let's look at the optimization of the pseudo substrate. If we look closely at the strain state of layer 1 InGaN in this relaxed InGaN on porous GaN pseudo substrate, we can see that before the regrowth, it was 50% relaxed, and after the regrowth, the layer 2 the layer 1 is shifted to the right, leading to a 70% relaxation with respect to gallium nitride. And layer 2 is almost strained to layer 1, which implies that these two layers move together as a unit on top of the porous GaN layer. And further analyzing this result, we can see that the relaxed InGaN base layer 1, which we grew initially strained to gallium nitride, is a problem, especially in terms of the morphology. So what if we replace this layer 1 with gallium nitride? If the elastic relaxation is due to the porous GaN underlayer, replacing the base InGaN layer 1 with gallium nitride, we should still have a compliant substrate, but without the V defects on the surface. So when we grew indium gallium nitride on this compliant GaN capped pseudo substrate, we were able to achieve as grown 65% relaxed InGaN layers. And that is when we proceeded to device development on these micron-sized pattern, which of course has to be a micro LED. The figure on the right is our first generation micro LED cross-sectional cross-section. On the left is what we have as the as-grown epitaxial structure. And we have used thin nickel gold transparent metal contacts as our P contacts and PCVD dielectric for sidewall passivation. We need to pay attention here to two different dimensions. The first is the tile size, which is this wider dimension, and that decides the degree of relaxation. And second is the mesa size, which is the actual device active region dimension. In the following slides, we'll be discussing results for devices with a mesa size of 4 cross 4 micron square, fabricated on tile sizes of 8 cross 8 to 20 cross 20 micron square. Our goal was to tune the emission wavelength towards longer wavelengths. So the first thing we did was change the tile size. As we saw before, for the same bias voltage, the narrower the features, the higher the relaxation. So when we decrease the tile size, we should be able to achieve higher relaxation, leading to a higher indium content in the quantum wells and thus a longer emission wavelength. Secondly, if we kept the tile size constant and changed the indium content of the N-InGaN layer and kept the growth condition of the multi-quantum wells and the P layer the same, we would be increasing the lattice constant of this N-InGaN base layer, allowing for higher indium incorporation into the quantum wells and hence longer emission wavelengths. So let's look at the results. But first, I wanted to illustrate what I would be calling the non-porous reference structure. A part of the porous sample, which I did not pattern into squares, was left non-porous, and upon regrowth, we were able to achieve on wafer GaN on sapphire reference results. So being on the same die on the same wafer, the difference between this device and the porous device is that this device was not tiled prior to regrowth. And so the tile size is not defined, but the mesa size is defined, and it is the same as the porous device. So we can compare them in a fair manner. If we take a look at the results, as expected, the non-porous device emitted at a much lower wavelength compared to all the porous devices. And among the porous devices also, there was a clear trend. This is a peak wavelength of emission versus current density. So at a certain current density, the smaller the size of the tile, the higher the relaxation and hence higher the emission wavelength. Moving on to the second variation, in which we changed the indium mole fraction of just the N-InGaN base layer, keeping the quantum well and the P layer growth conditions the same, and also the device size and the tile size the same. We could achieve a much larger redshift in emission. However, there was a problem here. We could not detect the electroluminescence of these devices beyond or below 60 amps per centimeter square, and the peak efficiency we could achieve at 100 amps per centimeter square was just 0.001%. So we needed to improve the device performance. Let's look at our process optimization, wherein we replaced the nickel gold contact with ITO, which allowed for a superior current spreading at the edges of the devices and also allowed for higher yields in our process run. And we also replaced the PCVD dielectric with ALD sidewall passivation, which led to enhanced luminescence in our devices. After the initial demonstration of devices, we wanted to demonstrate red emission from these samples while employing better fabrication techniques. And for calibration purposes, we targeted yellow emission for GaN on sapphire templates. And upon achieving that wavelength of emission, we proceeded with growth on porous wafers because we anticipated a wavelength shift from yellow to red on the same die. And as we can see, we got yellow emission from the non-porous layers. Here is again the peak wavelength versus current density. So for a certain current density, the emission was orange to yellow for the non-porous devices. And on the porous region of the die, we could achieve red emission. And this was a 6 micron cross 6 micron micro LED. The red micro LED was measured using an on-wafer electroluminescence setup with light being collected at the back side of the wafer. This device had an on-wafer EQE, peak on-wafer EQE of 0.2% at 10 amps per centimeter square, and it emitted 2.1 milliwatt per millimeter square area normalized light output power for a 6 cross 6 micron device, compared to the best reported and smallest Allen gap red micro LED, which emitted 1.75 to 2 milliwatt per millimeter square for a 20 cross 20 micron size device at the same current density. Although both these devices were measured on wafer, different measurement setups were used. The Allen gap device was measured from the top due to substrate absorbance, the InGaN device from the backside of the substrate, and at the same current density, the emission wavelengths were also different. Even though these factors make the comparison of these two results difficult, we believe that this comparison will help the audience realize the potential of the in-GaN material system for red emitting ultra small micro LEDs. And moving on to the comparison to the state-of-the-art in-GaN results, we demonstrated a higher efficiency figure for a much smaller device. We believe that this demonstration indicates the potential of red in-GaN micro LEDs for display applications and future commercialization of this technology. And pointing out something else here, we were also able to detect light down to 1 amps per centimeter square compared to our first generation red device. And with that, I would conclude my talk. Here's a summary. We have demonstrated a compliant GaN on porous GaN pseudo substrate demonstrating as grown elastically relaxed behavior in a micrometer scale regime. And we have also shown the impact of composition pulling effect on indium incorporation in multi-quantum wells and bulk in GaN films. We fabricated micro LEDs on these substrates, emitting at a longer wavelength when compared to devices grown on conventional substrates, which helped us demonstrate world's first red in GaN micro LED sized below 10 microns. Thank you for your attention. And with that, I would take any questions that you may have.
Hi, Shubhra. I had a question about when you replace the, I think the nickel titanium contact with ITO.
Mm-hmm.
Before you replaced it with ITO, how were you able to measure the light that was coming out of the device? Is nickel and gold, is that also transparent to some extent?
So I used 5 nanometer nickel and 2 nanometer gold. So at such thin, like at such small thicknesses, these metals are almost transparent. But as I showed here, the setup which we used, we collect light from the backside. So it doesn't matter what is there at the top. Does that answer your question?
Yeah, thank you.
Mm-hmm. So I had a question initially. Could they speak up and rephrase their question, please? I think somebody was asking about the slope of this line. Is that right?
Oh no, I was unmuted by accident. I'm sorry.
Okay.
Shubhra, could you go
Okay.
back to the composition pulling effect again? I was a little bit curious how that growth works on that.
Composition pulling effect, yeah. Mm-hmm.
So am I correct that the strain allows the essentially the relaxation of the next layer of GaN, in GaN rather?
So when you don't have relaxation, what happens is due to the strain in the structure, the indium content gets lower just to have a lower strain energy overall in the structure. That is only because of the lattice mismatch difference between these two layers. So if you have a biaxially relaxed in-GaN layer underneath, then the difference in the lattice constant is low. So the strain in the structure is low. That allows for higher indium incorporation. Does that answer your question?
Yeah, I mean, that's pretty much, that's straightforward. What is can you go over the effect of like using GaN instead of in-GaN for the template?
So the reason for our GaN still working is because it was, again, very thin. So now this is not our pseudo substrate. The pseudo substrate is the in-GaN which is formed above it. Okay, so now we are not trying to incorporate more indium. We are trying to just create a pseudo substrate. So this is kind of a super substrate, and then we are creating a pseudo substrate by growing it. So when we are actually growing our LED structure, the N layer is actually our pseudo substrate. So we are growing our pseudo substrate as we are growing our LED structure.
Interesting.
And the reason the GaN works is because it's thin. It's not as thick. So when it's thin, it is more stretchable.
Okay, thank you.
Okay, so I see a few questions in the chat. Let me start addressing those. So Vincent asks, how thick was your porous layer again? So the total thickness of the porous layer is 800 nanometers. And do you think with proper optimization, a porous device could survive a flip chip bond? Okay, so I think with proper optimization, you can pretty much do anything. So yeah, that is possible. Mhm. And next question is from Caroline. Did you cover the whole mesa with metal for backside collection? No. So that's also something that I did not perform, covering the whole mesa with light to improve the backside light extraction. So the on-wafer EQE that I show here, where is it? So this on-wafer EQE is also not optimized. We can potentially cover the device with metal or reflector or something like aluminum and get higher light extraction from the back. I did not do that because I wanted to take a picture from the top. So pretty lame answer, but yeah, I did not optimize it for backside extraction. Thanks. Okay, so Vincent has another question. If the porous scan layer is purposely separated, do you think the delaminated interface could be somehow polished to have 1.2 nanometers RMS surface roughness? Okay, so if I rip off this device and turn it upside down, there can be multiple ways to remove it. You can actually just follow, sorry, let me go back to the porous formation regime. You can actually just try during the electrochemical etch to remove the whole N plus layer so that you can just transfer it off to a carrier substrate from the get-go and grow on top of it. And polishing may also work. It's just I'm not really an expert in that, but potentially you can achieve a very smooth surface by polishing and getting rid of all the interface roughness coming off of these substrate removal. Yeah. Okay, any more questions? Okay, Lei Wang says, can you talk about the comparison between this technology and the current micro LED used in AR VRS for the cost performance? Okay, so currently in the AR VR, I think for red, for blue and green, it's InGaN, but for red, Allen Gap micro LEDs are used. We have few people who have interned at Facebook who have come back to UCSB. I think recently Ryan Lay returned from an internship there, and he, in his MOCVD talk, I think he mentioned it was really difficult for industry to scale the phosphide material system. So they are also excited about the InGaN material system. In terms of cost, obviously something which we are trying to do initially, when it's not mature, it's going to be costly. And the job of academia would be to help lower the cost and make sure that we can get it ready for commercialization. So that's one of the jobs that we have to address to lower the cost. Yeah, so that's my take on it. All right, so I think I have answered all the questions. So Chris, it's your turn.
Excellent. Thank you, Shubhra. So yeah, so 1 second here. I'm going to go ahead and actually share my screen for one quick shameless plug of an event we have coming up later this month. So before going through Chris's talk, I'm just going to briefly mention that we have the Quantum Industry Showcase coming up in just about 3 weeks. So this is essentially a network opportunity for anyone interested in learning more about opportunities in the quantum information science industry. So we'll have several different companies, including Google. I don't think we listed them here. Thor Labs, Honeywell, HPE, Oxford, will all be here, and we'll actually have different industry representatives talking about their experiences, such as transitioning from academia to industry and answering any questions anyone has. So if you have any questions, feel free to reach out to us and please register when you can. Thank you. Okay, so that out of the way, I'd like to introduce Chris Zollner from Nakamura's group. So Chris is, hold on 1 second here, I'm pulling up my bio information. 1 second. So Chris is going to talk about UV LEDs for disinfection. I think we'll go ahead and turn it over to him. Go ahead, Chris.
All right, thank you. And thanks, Shubhra, for that talk. That was really interesting. Hopefully I can try and have something interesting to say to follow up on that. So how does, oh, that's not the first slide. All right, how's that look?
Looks great.
Okay, cool. So yeah, so I'm going to talk today about my project, which is aluminum gallium nitride based UVC LEDs. This is a team project with a lot of contributions from all the people you see here. So primarily a sleek project these days, but also contributions from folks in the materials department and the ECE department as well. So I promise I'm only going to have one slide where I mention the COVID outbreak, because I know we're all sort of really exhausted and don't want to talk about COVID anymore. But as you might have guessed, UV disinfection and just disinfection technologies generally have gathered a lot of interest these days. Pretty early on in the pandemic, this was about this time last year, it was demonstrated that the SARS-CoV-2 virus can be inactivated using UVC light. So those are the wavelengths around 260 to 280 nanometers. The photochemistry here, I'm definitely not a chemistry person, but if you imagine a strand of DNA, in this case, it's 2 strands of DNA. It could also be a single strand. You kind of just ignore the strand on the right here. But anytime you have 2 neighboring thymine bases and you illuminate them with UVC light, there's some probability that they will dimerize. They'll just stick to each other, kicking out the adenine bases that they were previously attached to, and this pretty much renders this little segment of genetic information not replicable. So when this happens enough times, whatever cell has been illuminated is no longer able to replicate, and that leads to obviously a disinfection effect when you're talking about microbes. I don't know if anyone else has really seen this thing, but this is definitely something we've been paying attention to, that there have been a ton of basically fake products ever since the COVID pandemic, claiming to be UV LED disinfection products, like this one that you plug into your phone. So Josh, from whatever this website is that I pulled this from, is definitely right that as of right now, a tiny UV light powered by your phone is not currently powerful enough to kill bacteria. So this is probably a scam. Don't buy this because right now UV LEDs are extremely inefficient, and there's no way this is putting out more than a milliwatt of power probably. But in the future, we would like to have this sort of thing be a reality, or at least in general have UV LEDs for disinfection applications. So that's the motivation here. A brief history of UVC disinfection. It's actually been around for a pretty long time. It was first discovered back in the 19th century and was awarded the 1903 Nobel Prize for realizing that UV radiation could be used, in this case, for treatment of diseases, but just for disinfection generally. Starting in the 1930s, when you started to have really efficient and mass-produced mercury vapor lamps, it became popular in hospitals for air disinfection. Starting around the 80s, you started to see a lot of it in water disinfection, so municipal water, both for wastewater treatment, but also for drinking water. Starting in the 2000s, you saw a little bit more of this sort of a robot. It's basically just a bunch of UV lamps that you wheel into a room and blast the room with a ton of UV light. So this started to be used in places like hospitals and nursing homes and other places with health sensitive residents. Another important application here this is a schematic of an air duct, an air conditioning air duct. Actually, primarily the idea here is not to disinfect the air itself. The lamps aren't really powerful enough to do that because the air is moving so quickly, but they do disinfect the coils, so they prevent buildup of fungus on the coils, and that makes the coils run much more efficiently, reduces the maintenance cost on those coils. So that's that is actually one of the biggest markets for UV disinfection. Drinking water, of course, point of use, drinking disinfection is one of the newest areas that UV LEDs enable. And again, so last time I'll mention COVID. After the COVID pandemic broke out, we needed a way to disinfect PPE for medical personnel. So a lot of these UV LED based PPE disinfection products hit the market this time last year. So the point of this slide, I'm just trying to show you, this is an established technology. This isn't some sort of questionable thing that we don't really know if it works. I mean, UVC disinfection is really a very important technology, and there's a strong motivation to get a better UVC light source. So the state-of-the-art UVC light source, like I mentioned, is a mercury vapor lamp. It looks something like this. The color of the lamp mostly just depends on which what sort of a coating you put on it. So if you put a white phosphor on a mercury lamp, you just get your standard fluorescent lamp like everybody has in their house. And this slide is maybe a bit basic for this audience, but the trend, as we all know, is that you go from vacuum tubes towards solid state technologies. It's happened here for illumination. It also happened for digital logic, right? Computing, we went from sort of vacuum tube amplifiers to transistors. And the idea is we want to do the same thing with ultraviolet light sources. We want to move towards a solid state ultraviolet light source. The advantages being, as we all know, longer lifetime, in principle, higher efficiency, lower cost, instant turn on with no warm up and flicker. All the standard advantages that we're all well aware of for light bulbs, presumably will also apply for UV light sources. So some examples of modern applications or maybe you could say future applications that people would like to see. This is an airplane, and this current product, which is on the market, is another one of those giant robots that you wheel down the aisle and it blasts the cabin with some UVC radiation. Which is great, except that it leaves the vast majority of the cabin shadowed. So if no UVC light is incident anywhere that doesn't have a direct line of sight to your light source, then this isn't actually a very good disinfection solution. In a distribution of a large number of small sources, even if each individual source is quite low in power and maybe not so efficient, a distribution of many small smart light sources would probably be much better. So that's an example where LEDs would probably be better. Next up, for water disinfection, as I mentioned, sort of large municipal scale applications are pretty well established. The lamps are quite efficient. What we'd like to move towards is more miniature, maybe even portable or consumer applications. This is a product that's already on the market. So you're already starting to see some consumer applications for sort of residential drinking water with UV disinfection. People like this because they can, they don't need chlorine, for instance. You wouldn't want to be treating your wastewater with chlorine and then dumping that into the environment. But of course, the lamps are less efficient. They're less powerful. So we need to work on the efficiency. Another example of an application. So what's wrong here? What's wrong with this picture? Well, so first of all, it's a really terrible Photoshop. But second of all, there, nowhere in this picture is there really space for a UV lamp. You could imagine putting one maybe upstream, but if you want an on-demand point of use disinfection solution, you need something small. You don't really need very high power, but you need something that can instantly turn on and off. Preferably, and you can't really do that with a mercury lamp. It kills the lifetime if you rapidly switch those on and off. As I mentioned, chlorination is not so great. I mean, it works. It's an established technology, but there are plenty of reasons why we'd prefer not to be chlorinating our water. So let's see. And then, yeah, finally, just to really quickly mention again, so for portable consumer products, you don't really need high power anyway. You mostly just want low cost and lightweight. So you're really starting to see a lot of consumer products now with UV LEDs. But, you know, again, the power could be higher, the cost could be lower. There's a lot of things to work on here, but it really all comes down to efficiency. So hopefully I've somewhat motivated the need for a solid state UV light source. And we can move on to LEDs. I know this slide is probably a bit basic for this audience, but just to make sure we're all on the same page, right? Really the only material system that you can grow economically and reliably that emits ultraviolet light is the aluminum gallium nitride alloy. And, you know, as we all know, the band gap of the alloy determines the emission wavelength. So for this type of emission wavelength that we're shooting for, which is in this 250 to 300 range, we need basically at least 50% aluminum, if not higher. So we really are deep in the algan alloy range towards the aluminum nitride side. Just really quickly, some equations. As we all know, wall plug efficiency is the most important metric for really any device. We always talk in terms of efficiency, not just because efficiency is good, but also because, you know, if you go to industry and you tell them the efficiency is higher, you know, they won't really care. But if you tell them the power is higher, they'll say, oh, okay, high power is good. Or, you know, if you tell them the lifetime is longer, then they'll say, oh, nice, okay, good, you know, lifetime is longer. But really all of these factors, it's all about wall plug efficiency. Wall plug efficiency will improve, you know, lifetime, power, costs, really everything. Because LEDs are essentially a one-to-one light emission device, right? By that, I mean, every injected electron produces at most one photon. It's convenient to talk in terms of a quantum efficiency. So you can use the word quantum, which sounds fancy. So, you know, people like to publish academic papers with the word quantum in it, but it really just means counting efficiency, right? We're going to count up how many photons we get out for compared to how many electrons we inject. And then the other part is the electrical efficiency, and that's just a question of how much energy do we actually need to get each electron, or, you know, strictly each electron hole pair into the LED versus how much energy actually makes it into the photon. And then finally, the EQE we can further break down into light extraction efficiency. That's what this term is here. That's just a function of how transparent your materials are. This is a big problem in UV devices because pretty much nothing is transparent in the deep UV. But, you know, we'll get to that later. And the internal quantum efficiency, which is the radiative efficiency times the carrier injection efficiency. So the way I've drawn this device, I've sort of just drawn in an excess of electrons here and an excess of holes here. In reality, if you drive this device at high current densities, because in the nitrides, the holes aren't very mobile and there aren't very many of them, you will get significant electron overshoot into the P region. So instead of generating photons in the active region, those electrons will recombine non-radiatively in the P side of the device. So we call this overshoot, or more generally, just reduced injection efficiency. So that's also a very important one, which we'll come back to. So we grow these by MOCVD. Again, probably something most of you are familiar with. It's a vapor phase epitaxy technique where we introduce some process gas over a heated wafer. The heat from the wafer activates whatever chemistry needs to go on between those precursor chemical vapors. And the result is you get a deposition of a single crystal film on a substrate. Here's a cartoon of what the epistack looks like. We grow on aluminum nitride buffers. We'd like to grow on GaN buffers, but the lattice mismatch between GaN and aluminum nitride is quite large. So you can't actually grow these algan alloys on GaN without them cracking. On the other hand, gallium nitride is also absorbing in the UV, so we would need to remove it, and that's a little bit cumbersome. So you know, we need to grow an aluminum nitride buffer, and that's tough. Then we need to grow the N-type algan. That's also not trivial, but there are some pretty reliable methods for doing that nowadays. Then, of course, the active region is a pretty standard LED active region with quantum wells. sort of complicated p-type structure, including p-type gallium nitride. I just got done saying gallium nitride is absorbing, so you don't really want it. But as it turns out, the whole concentration in p-type algan is so low that really the only way you can make a decent electrical contact is using a contact to PGAN. So you sort of just have to have some PGAN in there, and you make it as thin as you can, but it's really tough to avoid that. And the light extraction efficiency is about 10% in a standard like this. So our approach in this project is to look at this equation and say, okay, we've got this list of contributions to the wall plug efficiency. Let's just go through them systematically and try to improve them each one by one. Right? It seems like a pretty reasonable way to approach this. So we'll start with the radiative efficiency. And what the radiative efficiency is all about is, so you've got electrons and holes in your active region, and you want them to recombine directly from band to band to emit photons. You don't want them finding defects, right, or traps and recombining there, because that won't really give you any light emission, or at least not any useful light emission. And you also don't want them to give this energy from the recombination event to another charge carrier, such as an electron in this picture. So that's called Auger recombination. So for now, we're going to focus on this one in the middle here, what they're calling trap-assisted recombination or Shockley-Reed-Hall recombination, which occurs wherever you have defects. And you don't want that. So what it comes down to, pretty simple, you just want to reduce the number of defects in your material. Point defects are important, but a sort of more interesting question is the question of extended defects, because those tend to be to exist in very high densities in aluminum nitride. And so this is a TEM image where you can see these threading dislocations starting at the bottom. So down here is the substrate interface, and this is the surface of the film at the top. And you can see these dislocations which thread upwards throughout the film. And once these generate, it's very hard to get rid of them, because they'll just thread up vertically pretty much forever, and they'll poke through your active region. And anytime a hole is close enough to a threading dislocation, it will just recombine at the threading dislocation non-radiatively. This tiny little arrow here that you can barely see, that represents the diffusion length of a hole in algan. It's quite short, which is good, because if your dislocation density is low enough, like it is in this picture, that the distance between any two dislocations is far enough apart that, say, a hole here doesn't see either of these dislocations, then that hole is more likely to recombine radiatively. So it's not like we need to completely eliminate all the dislocations. We just need to get them low enough that that they're much further apart than this very short hole diffusion length. So that seems doable. So that's sort of the first experiment I'll talk about here. So when you grow nitrides on sapphire, they nucleate via an island nucleation mechanism. And they do that because the sapphire is so dissimilar from the nitride that there's just no way you're going to get layer by layer growth. So you nucleate a highly disordered layer, which accommodates all of the mismatch and is full of dislocations. Then you heat up the reactor and deposit some more material, and you get larger islands. And the good news is that these larger islands are typically almost defect-free, because they're growing on essentially a fully relaxed layer. They're basically growing on a fully relaxed nitride layer. So the islands are almost dislocation-free, and they grow, and eventually they coalesce into a film. And really the only dislocations you get, for the most part, are at the coalescence boundaries between these islands, which are slightly misaligned. So the trick here is you want to get large islands. You want to get the largest islands you possibly can. That's tough with aluminum nitride because the aluminum atom mobility is very low, and as a result, it tends to form very small islands. So how can we get larger islands? Well, our approach has been, instead of using sapphire, to use silicon carbide. So we sort of just completely switch up the growth technology here. So instead of growing on sapphire and relying on a heavily disordered nucleation layer, we just nucleate directly on silicon carbide. It does have a 1% lattice mismatch, but it's not huge. It's close enough that you can get the nucleation of large islands directly on silicon carbide without this disordered nucleation layer. And as a result, you can get large islands. And there's some more details to this that I'm running a little bit behind, so I'll skip some of the details. But I'll skip this slide. So I have some experimental details here about how we measure stress during growth. But the point is, by changing the way we prepare the substrate before the growth, we changed the step size. And in this case, these are atomic steps. In this case, these are just sort of macro features coming from the polishing. By changing the step size on the substrate, we effectively change the island size, because as it turns out, in this case, the island size is mostly limited by the step size. And like I said, larger islands, lower dislocation density. We measured islands, it's hard to measure island size directly during growth unless you can do some sort of TEM, but you can measure island size indirectly by looking at the stress. So when the islands coalesce, they generate a tensile stress, which is proportional to the inverse of the island size. So anyway, long story short, higher tension means smaller islands, less tension means larger islands. And in fact, we can even get into compression because, like I said, there's this compressive lattice mismatch. So we're able to pretty much eliminate the tension due to island coalescence and actually get to the point where we observe that compressive lattice mismatch strain. And so, the good news, the takeaway for those of you who do epitaxy, here's the number that we got to. So this is pretty exciting, because if you do the math, this is significantly below the threshold needed, which again is set by the hole diffusion length. So there's also other benefits to reducing the compression, but let me just move on here. At this point in the talk, usually someone raises their hand and says, hold on, silicon carbide is absorbing, right? So, aren't you gonna have trouble with the light extraction efficiency there? So that's true. Silicon carbide has actually a similar band gap to GaN. It's not too different, and it does absorb in the deep UV. So Burhan, who graduated a few years ago, came up with this really nice process to remove the silicon carbide substrate after growth. This ends up actually being an advantage because there's no convenient way to remove a sapphire substrate, but you can actually remove the silicon carbide substrate pretty easily using a selective dry etch. And what that does is it exposes the aluminum nitride epi layer, which you can then roughen using some chemicals, and that enhances the light extraction efficiency. So here, if you're familiar with what's called the escape cone, long story short, if you roughen your sample, you can get significantly more light extraction because the emission direction becomes randomized instead of having this total internal reflection constraint. So using this technique, we've demonstrated some of the highest light extraction efficiency. So you can check out Burhan's paper on this, and so that's how we address the silicon carbide issue. We sort of turn it into an advantage, if you will. So anyway, so far we've talked about radiative efficiency, how we reduced one sort of defect. Of course, there are a lot of other defects that we also are working on reducing. And we also talked a little bit about light extraction efficiency, which we can improve by roughening. So next, I just want to take a couple minutes to talk about injection efficiency. This is a nice figure that Daniel Myers and Andrew Espenlaub put together. And, the takeaway is there's a lot going on here, right? So just because you have carriers in your active region, like I said, doesn't necessarily mean they're going to recombine to give you a photon. And importantly, they might just overshoot completely and go straight into the P-type material. And that's what we want to try to avoid. So in aluminum gallium nitride, similar to GaN, it's very difficult to get good P-type material. It's even harder with algan. But one thing you can do is you can use a superlattice where, because the material is polar, every time you have an interface between two materials at a superlattice, you get a sheet charge. And the result of this is that you get this sort of oscillating valence band where over here, you'll get a bunch of ionized acceptors, and then over here, the holes accumulate. And so every one of these little wells is a hole accumulation layer. And if the holes are, if these wells are close enough together that you can get some tunneling between them, then now all of a sudden you've got a p-type layer with a high hole concentration. So that's called modulation doping, or well, it's different people call it different things, but you could consider that a sort of modulation doping. There's other physics that goes on, you know, there's some optical advantages, there's some growth advantages that I don't really have time to go into, but there's a lot of advantages to growing superlattices. So, you know, why not try a superlattice? So this is the experiment that we did. Here's our epi stack again. Initially, back in the old days, we were just using a sort of uniform or bulk algan layer for our p-type algan. And the question is, what if we go to a superlattice? Right? And we want to be able to make comparisons without changing our average composition too much. So when I say, you know, a 45% composition layer, that could mean it's actually a 45% alloy, or it's a superlattice with two different alloy fractions that average out to 45%. So for the LED growers in the audience, you can look at this epi stack, but really the main takeaway here is we tried a few different types of superlattice layers, a few different uniform layers, and one sample that had a superlattice capped with a uniform layer. And the question is just, how is this going to influence our injection efficiency, right? Because the idea here is that we're not changing the active region. These devices all have the same active region, so the radiative efficiency should all be the same. All we're really changing is the injection efficiency. So if we look at the EQE, here's just another device schematic. If we look at the EQE curves, the red and blue curves are the 20% algan. Unsurprisingly, at 20% algan, it's going to be pretty optically absorbing. The EQE is low. If you go, excuse me, if you go to 45%, 45% superlattice, you get a really big enhancement, probably both coming from the light extraction efficiency enhancement and from the injection efficiency. However, if you go to 45% with a uniform layer, it's not even on this plot because it didn't even light up, right? So you just, there's no holes in this uniform 45% layer. You cannot get good hole injection from this layer. And then interestingly, if you combine the uniform 20% layer as a sort of contact layer with the superlattice, which will enhance your hole injection, you can get a pretty good EQE that's intermediate between the two. And if you look at the voltage is pretty much just as good as the full 20% sample. So in other words, combining both uniform and superlattice layers could be an advantage. So finally, one really important aspect of LEDs is called droop. That's the idea that your EQE is highest at low current densities and then gets much lower as you drive it to very high current densities. There are a few explanations for droop, especially in UV LEDs. People say that it's just coming from injection efficiency droop, which means that as you drive the device at higher and higher voltages, you get more and more electrons overshooting. But if we look back at our results, the devices with the best injection efficiency, right? So for instance, this green curve here, the device with the best injection efficiency also had the most droop. So injection droop is pretty unlikely. The next possibility is thermal droop. That's a pretty standard effect that is also seen pretty much in any optoelectronic device. So to rule that out, you just do some pulse measurements. So I have those data here. You can see from the wavelength data that we've eliminated the thermal redshift, which happens at high current densities, suggesting that we are eliminating heating indeed when we do this pulse measurement. However, the EQE curve is basically right on top of where it was in the continuous measurement. So that leads us to Auger, which is this recombination mechanism that dominates at very high carrier densities, as to me, probably the most plausible explanation for this droop, since we've ruled out thermal droop, and I believe we can safely rule out injection droop too. So that's interesting. Got some evidence for Auger, perhaps. So finally, I'll just summarize. I gave one example of a way that we tried to reduce the defects in our active region and enhanced our radiative efficiency that way. I didn't talk about the way we lowered the N-algan resistance. That's something that we're sort of still working on, and we've got a paper that we're hoping will come out soon. But so, we did do some work to improve the voltage on that end. The superlattice hole injection layers gave us some interesting results regarding injection efficiency. And finally, the thing that I didn't really mention in this talk is the active region itself, right? Which we haven't really had a chance to optimize yet, just because there have been so many other things to work on. But that's obviously the next step. And then eventually we'd like to get to a fully transparent tunnel junction device so that we can get topside emission in addition to the bottom emission. So with that, I ran a little over time. So let me just thank everyone for your attention, and maybe some people stuck around for some questions.
All right, thanks, Chris. It was a great time for anyone to unmute themselves or throw a question in the chat.
Yeah, so it looks like Caroline had a question in the chat. Have we looked at the P side thickness? So we've looked at that a little bit. I'm assuming you're talking about the P algan. It's pretty, it's not so sensitive to that outside just sort of the standard voltage penalty that you might expect. So the thicker you make the P algan, the more of a voltage drop you're going to get. So you want to have the P algan as thin as you can get away with. On the other hand, if it's too thin, you'll get electron overshoot straight through the P algan into the P-GaN. And that kills your injection efficiency. So that's the trade-off. It's not so sensitive to that. So we've used layers from sort of 30 to maybe 60 nanometers. And so I guess to answer your question, it's not something we've really looked very carefully at, but it definitely matters. It's important.
Hey, Chris.
Mm-hmm.
Thanks for the talk. It's a good talk. I have two questions. So one is, I'm just curious what the composition of your EBL is typically.
Yeah, it's usually around 80% aluminum.
80%. Okay, so it's like 30% above what your algan composition is?
Yeah. So the N-type layers and the cladding, that's around 65%, and then the quantum wells are around 45%.
I see. Okay. And so you mentioned how you're using a P-GaN layer on top of your P-algan because you're not getting holes, right? Because of the high activation energy. But I was wondering, did you look into how was the studies on using a tunnel junction on that contact layer instead?
Yeah, so that's something we definitely want to do. It's not something we've had a chance to try yet.
Okay.
There are a few results out there using tunnel junction. There are a handful of MB results, and now there's also an MOCVD tunnel junction result. So it definitely seems doable. The voltages are usually pretty high, and you usually need a P-GaN or at least a GaN interlayer anyway.
I see.
So
you can't have like a P-algan and algan tunnel junction
So I mean, in principle, you'd want to design one, and I'm sure there are tricks you can do that have to do with the polarization to get some sort of polarization enhanced tunnel junction, and that's what everyone's sort of working towards. But for now, all the results I've seen have relied on some sort of P-GaN. It's pretty thin, so it's unclear how huge of a light extraction penalty it is. But that's, as of right now, no one's quite been able to get rid of that P-GaN yet.
Fair enough. Thank you.
Yeah, thanks.
Okay, thanks everyone. I think we'll probably cap it now in case we have other people want to head out. I believe we have another talk coming up later in April, so please stay tuned for more advertisements on future talks. And yeah, I put a link also for the quantum industry showcase in the chat if people want to use that in the next couple seconds. We'll also be distributing some advertisements about that as well. So
yeah, I also want to point out that we were also going to have student poster sessions for the quantum industry showcase. So with prizes provided, so definitely check out the link and definitely reach out to us if you want to attend the student poster sessions. And also we're always welcome for you or to present your work at the Photonics Society student speakers, student seminars. So if you want to use this as a practice for your presentation for a conference or just show your work, don't hesitate to contact us at the Photonics Society. And thank you, Chris and Shubhra, for your interesting talk.